So systems of linear equations is what we're looking at now. And in these first few examples, we look at whether or not the given system of equations is linear, which is a pretty simple thing, but we put it in standard form just to make sure. Although it's obvious if it's not a lot of times, but if it is, we should make sure. So here we're given one that is in number 1. What we do is we add x1 to both sides and the bottom, on the middle one, the most simple one. But the standard form is, your constant times a variable plus constant times a variable for each of the variables, the odd ones, and then it's all equal to a constant. Is the standard form, which is a good way to check if it's linear. So x1 minus 3x2 equals x3 minus 4. You subtract x3 to get in standard form, so that's linear. This equation is linear now. And the final one, you just add 2 to both sides to get in that constant form. So now you have constant times a variable, even though it's most of the time just 1 times it. And the sum of them all equal to a constant. So this is a linear system because each equation is linear. Number 3, both equations are not linear, so it's definitely not a system. And 5, we have a nonlinear equation, so it's not a system of linear equations either. Product of 2 variables, it's not linear. Sine, like a trig function with a variable in it, is not linear as well. So that's looking at some examples of spotting a linear equation. So now we're just putting the system of equations in a standard form here as a general thing, which is very quick and easy. First one, add y, you get y plus z equals 6. Subtract, this time we're just swapping it around to make it easier. And we subtracted x here, and then we do the latter step by fixing it in standard form. So y plus z equals 6, x plus y minus z equals 0, and negative x plus y plus z equals 3. And here it's a similar story. You just have to put all the variables on the left-hand side and the constants on the separate constants on the right-hand side. Yeah, this stuff's pretty simple. And here's one showing that the system has a solution indicated. This is more of just a refresher of how basic algebra 1 and 2 works, like with solving a system of equations and all that. This is more of a view, although we solve it in a slightly different method here when we get to that. Here we're just given a solution though for these 2 examples and plugging it in. So 2s, s, and s. We'll see pretty soon that means it's an infinite solution type of system, but that's what it's not, But so either way, we're just plugging these x, y, and z variables in. So x equals 2s, y equals s, and z equals s. Good. And it simplifies down, like 2s minus 3s plus s. That's 2s minus 3s is negative 1s, so negative s, plus s, that's equal to 0. Same thing here, same thing here. 2s minus s, just 0. So we get 0 equals 0, 0 equals 0, 0 equals 0, so it checks off. Check mark. Here we're given 1/2 plus s, 1 plus 2s minus t, and st. So 4 variables, so we have to plug in. So you plug it in, and then I cancel out as I show here. Close note. But it eventually simplifies down to just 1 equals 1, 0 equals 0, and 3 equals 0, 3. 3 equals 3. Here's one. Solve the system in exercises 15 through 17. So we're just solving a system now, and I'm going to explain very quick the basic process. But first look at the example. So x minus 4y equals 1 and negative 2x plus 8y equals negative 2. we can do equation 2 plus 2 times equation 1, and we get x minus 4y equals 1 and 0 equals 0. And this is like sort of like very close to the old school style where you'd add different equations to each other, like products of them. Let's subtract. So infinite number of solutions is the case, and you'll see real quick in this is basically one example of the Gauss-Jordan method, which we'll explain real quick. But 0 equals 0. It's an infinite number of solutions. So we let y equals parameter, which is y equals s. Here. Because that's the second row. And we have x already here. And then we do x minus 4 times s because it's x minus 4y equals 1. So it's x minus 4s equals 1, so that means x equals 1 plus 4s. So the solution is 1 plus 4s and s. And it's a line. It's infinite number of solutions in the form of a line, which stretches in two directions infinitely, as you know. It has the two arrows pointed. It's called the Gauss-Jordan method, and you use three things. You either multiply one equation by a constant that's not equal to 0, so c does not equal 0. Swap two equations, and add, or you can also add to one equation c times another equation, which we did. We did equation 2, we did c here, plus 2 times equation 1, and that's all we had to do. And the point is, you bring the system to the form x1 equals s1, x2 equals s2, and xn equals sn, where n is equal to the number of variables or whatever. In this case, there's 2, so there's x and y. You can have x1, x2, etc. as well. You could have x3, x1, x2, x3, x4. You could have x1 to x5, x1 to x10, you know. It's really unlimited, in theory at least. Although you don't see extremely complicated things in the real world like that, at least as far as linear stuff goes. So a lot of times you focus, and especially in a math course, you focus on only 2, 3, or maybe 4 variables usually. Right away, just for simplicity's sake, so it doesn't take forever to solve. But here we brought it to that, well, we brought it as close as we could. You can't really simplify this any further. You have 0 equal to 0, and the one equation left, x minus 4y equals 1. And this method is more used for in the next section than anything with a matrix, but this is a good introduction to it to get used to it with a couple examples. But no, 0 equal to 0 is a special case. You know, this is what you wanted to get to, but if you get 0 equal to 0 in one or more rows, it's an infinite number solution, so you get parameters. You let the ones that are 0 equals 0 parameters, and whatever, you simplify everything else first. But as soon as it's as simplified as you can get, you're really stuck with what you got and have to substitute in to get your last remaining variables. So here's one that definitely, you know, we do as well with Gauss-Jordan. We have 4 variables here. So we have equation 2 minus 2 times equation 1, and equation 3 plus equation 1. My strategy is to eliminate as much variables, like always try eliminating several variables if I can, as quickly as possible. And then you can clean up the rest in a relatively easy manner at the end when you've got you got a lot of zeros in place. You know, eliminate a lot of the variables in each equation. So you only have 1 or 2 in each. That's how I approach it. There's always usually more than one way to simplify a system if it's anywhere near complicated. But you know, some ways are more efficient than others, but the point is that you understand what you're doing and you get it down to simple form. As simple as you can get. So here we do equation 2 minus 2 times equation 1 and equation 3 plus equation 1. And this gets rid of some variables. We basically clear out the whole column, except basically in this, like the 4 equations, there's only one with x1 in it. So that kind of solved that issue, so we already have the first part. Now, we have to keep on cleaning up. As you can see, it's like equation 3 plus equation 1, that's negative 2 plus 1. So it just becomes negative 1 times x2, you know. This is equation 2 minus 2 times equation 1. So in this column, it's 3 minus 2, basically. You know, 3x2 minus 2 times x2. So you just get x2. And the first row basically is the second row, so another saying, so 2x1 minus 2 times x1 gives you just 0, so we get rid of it. And that's the whole thing you do for everything. Like every time you do this, you subtract or add rows against each other is the most common way to do it. Like row swapping's more of if you did in a little bit, you know, you did in a different manner. I don't, you know, row swapping's not as common, I don't think, like it can be, but like, yeah, you don't really use it as much. It's the least used of the elementary operations in my experience, at least. At least when solving a system. But no, the next step after we've gotten us saying in brown now, equation 4 minus equation 3, because this works very nicely. You get 0 equal to 0. But we can further simplify. So we have equation 1 minus equation 2, for instance, and that gives us x1 plus 3x4 equals 2 just. So that gets rid of x2 and x3 from equation 1. And equation 3 plus equation 2, well, negative 1 plus 1 is 0. Negative 1 plus 1 is 0. 2 minus 2 is 0. And 1 minus 1 is 0. So 0 equals 0. So we have very quickly simplified this down. About as much, we're about done almost. Yeah, that's where we end the simplification. So we have two parameters. We have x4, we can set it equal to s or t. You can set them equal to either one. Like it doesn't really matter at the end of the day. It's parameters. I don't think anyone would really care. But so x4 equals s and x3 equals t. You might see it the other way around. Regardless, you just keep consistent with this. It's whatever you choose. So x1 plus 3x4 equals 2 is from here. So that means x1 equals 2 minus 3x4, and then we plug in s for x4, so it's x1 equals 2 minus 3s. And we have x2 plus x3 minus 2x4, x2 plus x equals negative 1. That means x2 equals negative x3 plus 2x4 minus 1, and then we plug in values for x3 and x4, which is s and t. So negative t plus 2s minus 1, or however you arrange it. So the solution is 2 minus 3s, negative 1 minus t plus 2s, t and s. And the solution is a plane. It's a plane if it's two parameters. If it's one parameter, it's a line. And if it's just otherwise it's just a point. It's a point if there's no parameters, like a single point in space. Yeah, point, and then line was one parameter, and plane was two. And it keeps on, more and more. It becomes higher planes and stuff from there. Okay, now the given equations represent planes in R3. Describe the region, if any, that is the intersection of these planes. So this is having us define what the intersection is exactly between these three equations, is essentially what it's asking. It's just a fancy way of saying it. You're basically asking you to figure out what the solution is and how you would, if it's a point, a line, or a plane. That's basically what it's asking. But okay, so you have your equations, and then we do equation 2 minus equation 1. So that gets rid of x here, so it's just 1x in the three equations. Then we do equation 1 minus equation 2, and equation 3 minus 2 times equation 2. And that simplifies it further. So equation 1 minus equation 2, we have just x plus 2z equal to -9, and we have other one 5z equals -12 for the other equation. Then you can do probably several things, but I chose to do equation 1 minus 2/5 equation 3 because 2/5 because 2/5 of 5z is just 2, so I'm subtracting basically 2z's then, so we get no z on top. And equation 2 plus 1/5 times equation 3, same deal, eliminating it so that we get in a simpler form. From this we just get x, y, and 5z on the left hand side, and then we have equals these things. And simplify it down. Again, we do 1/5 times equation 3 as well. Yeah, because we have 5z, so it becomes just z. And you add together all these things, and you get -21/5, 13/5, and -12/5. It's just math at that point. Yeah, as you can see, x, y, and z, so it's an exact format. So when this is when the Gauss-Jordan method works perfectly. You get it, so it's in a nice plane like this. Yeah, in x, y, and z only. And so if it's just these coordinates and it's a point, so because there's no parameters, as I was saying. And the other condition with Gauss-Jordan method is when there's no solutions, and that's when you have an equation that has 0 on the left hand side, so 0 equals like 1. That's not possible, so it's no solution. Oh yeah, find the value of c such that the system has a solution other than 0, 0, 0. So in this one we have to do some Gauss-Jordan method, or simplify. You don't have to do it. You could probably, because it's not like, but that's probably a good idea to practice more with it. So first, 2 times equation 1. You get 2cx plus y equals 0. And there's probably a better way to do it than what I'm doing, but this is one way. Because we have c times x plus 1/2 y equals 0. And 2y minus 4, that c variable is going to make it annoying, but we'll mess around. So you just multiply by 2 to get it so it's integer. So 1/2 becomes 1. We just have y. So then I do equation 1 plus equation 3. Which gives us 2 times cx. Yeah, so equation 1 plus equation 3, because it's 2x minus y equals 0. What it becomes is it just gets rid of the y, so it's just 2 times c times x plus 2x. So 2cx plus 2x. Basically. And we still have some, so we can rearrange this to be just 2c plus 2 times x. So it's just everything, it's basically x times 2c plus 2. Distribute it out to x basically. And then arrow down, we swap rows, so we get 2c plus 2 times x equals 0, because Gauss-Jordan method has that at the bottom. Usually like you're saying. And we can do 1/2 times equation 1 and 1/2 times equation 2. So it's just x minus 1/2 y equals 0, y minus 2z equals 0, and 2c plus 2 times x equals 0. So the point is, it probably did a little bit more work than needed, but so 2c plus 2 times x does not equal 0 means no solution, like I was saying. The right hand side is 0. So 2c plus 2 times x has to equal 0, basically, or else there'll be no solution. So you have 2c plus 2 times x equals 0 means that x equals 0, which is one solution where everything becomes 0, essentially. Yeah, everything is equal to 0, and so it's x equals 0, y equals 0, z equals 0, which is the one solution that says that it does not want, it wants another solution. So 2c plus 2 has to equal 0 then. So that means 2 times c equals -2 because it's step 2, and then divide by 2, it's c equals -1. And that's the correct answer. C equals -1 will give you it. that'll give you a solution other than 0, 0, 0. It'll be infinitely many solutions technically, because you'll have a row that's 0 equals 0, but it's a different solution than 0, 0, 0. And that's all for this section.